Good, a little bit faster today. Today we're going to be doing some advanced clicking. In a few minutes, get your clicker out. We're going to be on frequency DD, and Darian is going to show you how to do that with the alternate display. But before we get to all that, I want to go over a couple things with you. A lot of you have registered through web courses. That is what is required. If you've registered by today, by about, let's see, we get out of here at 1:20. So let's see, about 1:45. I won't get to synchronize the roster for another 20, 30 minutes. So if you get registered up by 1:45 or sooner, you'll get a bonus point. Thursday morning is the beginning of official clicking. So today we're going to be doing some practice type questions, and we will be doing some scientific questions after the first couple. Thursday morning it'll all be regular questions. So make sure to only do that in web courses. If you were registered last Thursday, you have a bonus point already. And I imagine some of you have noticed that in the grades page, which is good. You know what? Now that I'm looking at this class, we're going to have to bring everybody in. On Thursday, I'm going to restrict the class from sitting in the last 3 or 4 rows back there, simply because I want everybody forward so that the clickers work without any headaches. So we're just practicing today, but on Thursday it'll be for real. So you guys in the last 3 or 4 rows, make sure I'll have everything restricted on Thursday. Be ready for it. Same thing, you guys on the left and right sides. Yo, in the back. Yeah, you're going to be moving forward on Thursday. All right, so just, I know some people like sitting in the back, but all right. So, okay, I want to talk about posting discussion questions. It can be very helpful for you and for me because it is very efficient for you getting tips about anything that you want to talk about. And so here's an example of a student that messaged me with the messaging system in web courses saying, Dr. B, where do I get an iClicker? Because the bookstore, when they messaged me, the bookstore was out. Anybody buy one today at the bookstore? I did. Yeah, okay, so I guess they got a bunch in there. Anyways, the student, and I said, look, I don't really know, but if you post a question in discussions, somebody will answer, and somebody did actually. Now, when you're starting, any of your topics, I want you to remember a couple things. First of all, if you look down at the bottom, this screen here shows the student, or let me get my cursor over there. There we go. This shows the screen as it would look pretty much the way a student would when they're starting up the questions. I want to draw your attention down here to these options down here because they're kind of important for a class like this. First of all, I want you to activate allow threaded replies. All right, so when you're doing your thread, whether it's about, acceleration or Newton's law of gravity or homework 7, where is it, anything like that, allow threaded replies. And that way, the discussion will have a little bit of internal structure, and without that, it's just a hodgepodge of people answering, and who knows who they're talking to, all right? And a lot of threads will get really complex, really well subscribed and answered either by me or Darian or one of your classmates or perhaps all 3 of us or all of us. And so threaded replies. Also, select the liking option as well. And if you can do that, those two things, that will make the discussion area much more efficient for you getting the message. And you don't want to fail to get the message. Speaking of messages, we have a stack of, for those of you that added Thursday night, this is your first time in lecture, we have a stack of green syllabus handouts. You can grab it at the end of class today, up here in the front, over here by Darian's side of the front station here. All right, so allow threaded replies, allow liking, and things will be very efficient. And then you don't have to message, then I don't have to read 700 messages. Hey, Dr. B, what about homework 7? You know, because it'll be in discussions. You'll be able to check it for yourself. All right? And it'll be more efficient. And for something like iClickers, I don't know the answer, but other classmates will, and so it'll work out nicely. And also the fact that there's probably other students with the same or very similar questions. All right, another factor I want to draw your attention to is just the title of the thread. What do you call it? Well, this one is not too bad. I told the student, make it specific. So the student wrote, where to buy an iClicker. And that's helpful. If you just type in, you know, something generic like, help me, okay, it's heart-wrenching. I'm going to respond to it. But for somebody that doesn't have any feelings, they're not going to have a clue what you're asking about. All right? If they have their own question, you're going to force them to go in there and ask, you know, see, now what's this person asking about and stuff. So, but if you label it very specifically, you know, like, how do you get the velocity in homework 2, question number 7? Or something like that, then people will see that, oh yeah, I know how to do that. And they'll post a reply. Or, oh, I want to find that out too. And they'll read the replies and maybe, you know, get your heads together. And this way, the discussion areas can become real beehives of activity for studying together and stuff. And I highly encourage you to do that. But I don't want you to type any that's supposed to be personal information. So, like your grades, the only restriction on discussions is don't post anything about your grades because that's considered private, and I have to follow very specific rules, Alex, about privacy. It's called the FERPA regulations. And so for instance, if you send me an email, I'm not going to answer it because I can't talk to students about grades and stuff like that on the email. So I just don't respond to emails. But messaging inside web courses, yes, I do. All right. So if you have something specific and personal, you know, like if you have to have an excused absence, anything like that, that's okay for messaging. But if it's just like, how do you get question 7 on homework 5, then that one is better for discussions. Okay? Don't put your phone numbers in there either. And I'm not looking at anybody, and I'm not saying that there's any maniacs in this class, but I'm just saying. All right? Don't put your... And if Darian sees it, and if I see it, we'll delete your entry, and we'll give you a message. Don't put your phone number, you know, we'll just kind of, you know. So don't do that. All right? And things will be better. Okay, so check allow threaded replies, allow liking, and make the title descriptive. All right? Any questions about any of that stuff? For those of you that are ed majors, secondary ed, elementary ed, you may be thinking to yourself, and the rest of you may be thinking, why does Dr. B always wait? after you ask for questions, like I just did? And the answer to that is I follow the 15-second rule. And for those of you that are heading into education, it's a good rule to remember. Whenever you ask for questions, give the students 15 seconds or more. And usually, if there is a question, it'll pop up in 15 seconds. You know, somebody will debate, oh, should I raise my hand? Am I going to be embarrassed? And it doesn't always work, but it works most of the time. So when you hear me, and here's 15 seconds, starting now. Stop. That's 15 seconds. It may seem like an eternity to you. You may feel awkward, but that's why I do it, because I want to get questions and draw them out. All right, get your clickers ready. We're going to do some special iClicker techniques. We're going to be doing short answer. Okay. And we're going to be typing in some actual words and symbols. Now, when we start this question, hold on, Darian, I wanted the students to see that. Go ahead and stop the question. Okay. Stop the question. And I will delete it later. Go ahead and start it. But don't click out of that screen.
It doesn't.
Oh.
Yeah.
New session. Hold on a second, we're trying to get this. All right, short answer. This mouse up here is a little bit, it's a little bit pokey or something. Okay, now leave that up. All right, so you're going to be using up and down arrow keys to select a letter instead of a number like we did last time. And then you're going to use the right arrow key to move to the right and add in another letter. All right, and you're going to be typing in words and symbols and stuff. Okay, you can actually type in numbers if you want, but that's not part of the answer this time. And then when you're done with your string of letters, whatever it happens to be, then you have to hit the send key, all right? And we're going to start it in just a second. Do you still have a question? Go ahead.
My iClicker won't allow me to connect with the...
All right. Darian, switch to the auxiliary power. All right. Now here's how you deal with that. If your clicker's not if this is the first time you're using it in class, you hold the power button down until the rectangle in the upper left flashes, and then you type in DD. All right? And then you'll get the Go Nitro message, and then it'll say ready, I think. All right? You got it? All right. Raise your hand if you got Go Nitro. All right. Good. All right, let's go back to regular laptop. Now, I want you to hit the refresh key for safety. Okay? And you're in the question now, and it should read the letter A on your screen. Now, if you go up and down, you'll be able to select different letters. And when you get the letter you want, and I'm going to tell you in a second what to type in. Okay, when you get the letter you want, then you type the right arrow key, and then go up and down again and select another letter. And then go to the right and select another letter. And go back to the left if you want to change a letter. That's fine too. But then at the end, you have to hit the send key. All right? Now, here's your first question. Very simple. Type in your middle name. And if you are a person that does not, listen to all that clicking. Nice. If you're a person without a middle name, and there's some of you, just type in Bob, B-O-B. Alan, J. Let's see some more of the other ones here. Anthony. Hey, Anthony. It's hard to see.
Oh,
Grace.
it's not scrolling down well because people are submitting new ones.
Yeah, that's all right. Alex. Jean. Good. I'll give you 30 seconds to finish. And don't forget to hit the send key. All right? Now, we're just practicing today. So if you blow it, it's all right. If you misspell your middle name, it's all right. It's not a disaster. But what you're looking for is a check mark. You want a Go Nitro message to start. And then when you hit the send key, you want to get a check mark. Okay? Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, go ahead and. Our thing is not. Yeah, that thing is. You know why it is? It's the surface is probably, the desktop is probably greasy. So just use this one. Okay, can you switch to the, yeah, let's look at some of these answers. Now, my spreadsheet is going to list all these different, whoops, Brooke, you typed in the letter Q. I don't know who that is, but Compton, Curtis, Elaine. Are you using the track wheel? Mm-hmm. Yeah, good, that's how to do it. Aaron. All right, so there's a bunch of people. Let's see if there's any, are there any Bobs up there? Ooh, a bunch of Graces.
Now it's doing the thing again.
This scrolling mechanism is. There we go.
There we go.
11 Bobs. Nice. And a BQB for bonus. All right, so anyways, this is very simple task. Now, this is not a physics question. Type in your middle name. All right? So go ahead and switch back. So that was an easy one, but let's try another one. And this one's going to be significantly different. It's not your name. It's a what I call a sentence formation task. I want you to create a sentence from the symbols in the code table. So for instance, type in ZATRWO to represent this lovely sentence. Zombies always take revenge with Oreos. Right? So this is kind of goofy, but go ahead and just type in a good sentence. And enjoy it. We'll have a regular science related one of these next. And let's see, and don't forget to hit the send key when you're done. And the length of your sentence is oh my goodness. I see a lot of Z's in here. That kind of concerns me because there's a lot of zombie, I guess people are worried about zombies for some reason. And Darian's up here going, yeah, Dr. B, that's true. At any rate. Okay, 30 seconds. Get in your answer and see if we get any goofy ones. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, we've got 101 displays, 101 replies, 0. Go ahead and click. All right, let's display this. All right, now this is what those codes, it's a string of letters, it's a code, and it can be decoded. And when you're doing this on an exam, I'll have all these in a spreadsheet, and I'll be able to put them back together into a sentence. Let's go down a little bit. All right, stop there. AEKWOT. Always eat crinkle cut French fries. W. With Oreos. T. Take. Good. Crinkle cut fries and Oreos. Let's go down a little bit further. Go see the all the way down the. Whoa! Somebody wrote a long one there. Let's go get some Z's. You see, everybody's got a bunch of stuff in here. And now there's my sentence. No good. No, that's not. Type it in mine, everybody. All right, let's try ZATSC. Zombies always take some chickens. Ooh. Yep, somebody spelled the word zombie. Anyways, okay, back to the regular laptop. That is just a fooling around example. Now let's try a serious one concerning nature and physics. And this is one that Professor Galileo might ask. My students, create a sentence about laws of nature from the symbols in the code table below. All right? Now, I want you to think, and I want you to write down your code string and also your sentence. And consider this the first part of today's notes, all right? Because we're going to be talking about Professor Galileo. And actually, this is the reference for this is the introduction in the e-textbook. All right? So think. And I'll just mention to you again that when you're doing this, as you probably will at least once or twice on exams, this might be a 3 or even a 4-point question. But it might not be this particular question. It might be, about electrons, or it might be about gravitation, or, some other thing. And the nice thing about this, actually there's several nice things. One is I can read every sentence. This is equivalent to a written test where you write in a sentence. You answer a short answer question on a written test. Now there's 300 of you, and there's 200 of you, so I wouldn't be able to do it physically if everybody were to turn in a written test. That's why we use Scantrons. But we can do a sentence equivalent in this way, and I can read I read everybody's sentence. And I give you 4 points, or 3 points, or 2 points, 1.0, depending on if it's righteous or semi-righteous, or if it's incorrect. All right? But there's something even more important about this. I'll wait until you guys are finished. And I can see that you guys are doing a great job. And don't forget to write down your code in your notes, and also the sentence that you intend. Create a sentence, a true sentence about the laws of nature, because that's what we're talking about. All right, 30 seconds to complete. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, type your, okay, that's it. Darian quit it before I was ready, but that's all right. Go ahead to the display, please. All right, now let's take a look at some of these answers. All right, and go down to the middle of the list somewhere. Everybody's starting with A. All right, that's good. Stop here. Let's look at the second one, HQLVD. Okay, that stands for scientific experiments apply observations and. Okay, actually, so that would be partial credit because they ended that sentence with and. They might not have wanted to do that. Let's look at the bottom one, JCHV. Just and if I were doing this on a test, I would look at all of them. I turn them back into regular English sentences. And it's, the thing about this, they're not going to be, when I turn them back into English sentences, they might not really be very graceful. So you're not able to write a sonnet as graceful as Shakespeare or anything like that. But I can still figure out what you're trying to say. JCHV. Okay, J is we explain scientific observations. Hey, that's not bad. That's a true sentence about laws of nature. Let's go down and find another one. That one would get full credit. Stop there. JNYHF. J is we. That's interesting. A lot of J's. That's good. We can understand scientific rules. That's not bad. We can understand, and that's actually a sentence. We can understand scientific rules. And notice, only one person typed that in. Now, I'm not going to ask for a show of hand of who that was, although I can figure it out. But let me give you the second, and I want you to write this down. The second important thing about these kinds of questions is this. In a class like this of 200, there can be 200 answers, all of them different, and all of them correct. If you think about it, on a multiple choice question, I have to write the question, and I have to supply the correct option, A, B, C, D, or E, and then I have to type in a bunch of, false options, some close, some not even close. But you're on a multiple choice question, you are dancing to my tune. I write everything. You respond. But this task, you write the right answer, and I've got to study it. And so this one allows for creativity, and it actually allows me to see into your mind, your so-called mind, a lot better than a multiple choice question. So these are really valuable to me. They're tough to set up, and we won't do them a whole lot, but when we do them, they're very, very interesting. For instance, look at this. Look at all the people that have J for the first. Even, think about it. What's the first thing that comes to your mind? We. See, you're already thinking of yourselves as scientists. We. I got you right where I want you. And that's a significant finding, just even the first symbol that you send in. We. All right? And so when we get further into the semester, occasionally I'll bring out questions of this type. All right? And they're really nice. They're really meaningful. Now, this one today, I'm going to give everybody points for this, so don't worry about that. All right, remember, this is practice today. But Thursday, if I ask you a question like this, I'll grade it. I won't be able to grade it immediately like multiple choice, but I will grade it, and you'll get points based on whether you're answering correctly. All right? Now, we have some more clicking to do, so let's try another question. And, you know, I have no explanation for this photo. I found it on Reddit, and it just looked a little bit funny, so I put it in there. Anyways, hit the refresh key. I put by the way, if I don't have any photo or illustration, I just put in something just to, fill the screen up with an image a lot of times. Hit the refresh key. We're switching over to multiple choice. Okay, and so whenever we switch one way or the other, we have to hit the refresh key. Okay, so you should it should say ready or something. All right. Question 4 for today, multiple choice, A, B, C, or D. And see, here's another example where I just put in an image that I like. This is an astronomy image, actually, a nebula, a supernova remnant. But it's pretty. Okay, 30 seconds. How many we got? We got almost everybody. Mm-hmm. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, the correct answer is numerical and geometric patterns. And actually, 87% of you got that one right. That is definitely appropriate for us because last time we were talking about the nature of this thing that we do, searching for the truth. So let's get back to that now. We were talking about learning, trying to find that which is true. We talked about Aristotle, Augustine, and Aquinas, their definitions of the truth. And the last one is pretty good, that towards which the intellect tends. And in every field of human endeavor, there can be different criteria of truth. Now, we're going to be talking about the scientific enterprise as begun by Galileo. But if you think about it, a love letter, you want to know that it's true. I mean, that's your sense. You don't want to be deceived. So if you're Belle writing a letter to the beast, you want to, the beast wants to know if it's true. Court of law, yeah, completely different. You judge that, for instance, with the hearsay rule. And if you've ever watched, like Law and Order or something like that, inadmissible evidence, that's hearsay. And everybody knows you can't do hearsay, because it's not, except there are exceptions. A statement made under belief of imminent death is admissible. It has the presumption of truth, and therefore, in a court of law, you can introduce it, and under the presumption that it's true, a deathbed confession, nobody's going to lie. The presumption is nobody's going to lie on their deathbed. What would they gain from lying if they're about to die? And the second another exception is statement against interest, where you actually make in court, you say, You make an admission that yes, you did bezel those funds, or yes, you did steal that car, or some admission against your interest. The presumption is that it's true. We have all these presumptions. In the court of law here in the United States and in many countries, we have this principle: you're presumed innocent until proven guilty. That's a presumption. Right? So everybody that goes to the courtroom, presumed innocent until proven guilty. All right? That's why they let criminals at court wear a nice suit. They don't let them go in there with their jail clothing on, because that would be what do they call that? Prejudicial. All right? So they let them wear regular clothes if they want. Okay? Another presumption is deathbed confession, presumed to be true. Statement against interest, presumed to be true. Now that's in a court of law. There's other rules of evidence. You go to law school, you can learn them all. The prosecutors and defense attorneys got to know them all. And the reason I bring that up is because Galileo established for us the rules of evidence, if you will, for something called physical science, the science of nature. So let's look at what he proposed about 400 years ago. Galileo was an interesting guy. He was very, very, he was like President Trump of his day. Well, he wasn't a president, but he had a big mouth, and he talked a lot, and he wrote a lot. In those days, people wrote, they didn't go on TV. He didn't have his own TV show or anything like that, but he wrote a lot. They wrote a lot of books and pamphlets and stuff. He was what we would call a controversialist. And we have those in our day. And he was also pretty smart. Here's what he wrote. Philosophy is written in this grand book, I mean the universe, which stands continually open to our gaze. But it cannot be understood. See that? We're trying to understand something. It cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. Okay? And so the scientist observes his world and attempts to answer questions about the things that he sees. And for instance, is there a pattern in what he sees? He's looking into this grand book. And this is page 9 from the introduction. Is there some clear interaction of the object that he's observing with other objects? For instance, the baseball. A baseball is on its flight towards the outfield is interacting with the gravitational field of Earth. It's in free fall. What will be the future state of the things that he sees? He wants to predict the outcome. Will the center fielder catch the ball or not? Or is it a home run, for instance? So, he figures, all right, at time t equals 0 down here, where the baseball starts its flight, and how long does it take to get up there? So he's trying to predict this future state, and then he wants to present his findings so that so he could call up Darien on the phone and say, all right, here's my findings, and you're the Trigmeister, and I want you to study this. And Darien will say, okay, Galileo, I'll study it. And she'll be able to do it. Now, whoops, I went backwards. Here's an example, this big fancy formula. That is a compact way of expressing Galileo's knowledge of motion. And this equation, I'm just throwing it out there at you right now, but in a week or so, we're going to understand everything in this equation. It looks like a bunch of symbols and gobbledygook right now, maybe, but eventually it's going to make a lot of sense. And that's our job for the next. And here's what Galileo said about that. This is the second part of this quotation. The book of nature that stands continually open to our gaze, it is written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures, without which it is humanly impossible to understand a single word of this book. And without these, one is wandering around in a dark labyrinth. All right? And that expresses his conviction in the court of law that we know as science, physical science. The school of Galileo, the rules of the road, the rules of evidence are, if you're talking about something, it's going to have some kind of mathematical backbone. It's going to have some kind of a mathematical description. There will be some kind of mathematical pattern. Are you writing this down? If you want science to judge your statements as true, you better at least have in reserve somewhere a math, or be able to describe the mathematical backbone of what you are talking about. Now that formula up there is the mathematical backbone for free fall. You hit a baseball to the outfield, that explains half the motion. All right, that's the vertical, that's the equation for the y coordinate, the up and down part of the motion. And the other part of the motion heading out towards the outfield sideways horizontally, that's got a different equation, a little bit simpler. Matter of fact, we're going to find that equation right now. So let's talk about motion. This is the first thing that Galileo tackled. And the choices that Galileo made are, I can't overemphasize the fact that what he chose to study has determined everything. And he didn't know it at the time, but he was making choices that even Albert Einstein had to deal with 400 years later, 300 years later. You know, Galileo was writing in the early 1600s, and Albert Einstein was writing in the early 1900s, 300 years later. And the decisions that Galileo made, Einstein himself and all of us to this day, we're still dealing with, and we're still following his lead, if you will. For instance, velocity. Velocity is defined as a speed and a direction. And with a speed and a direction, you encode the motion of an object so that you can predict its future state. Remember, Galileo in physical science, not all of it, but much of it, is trying to predict a future state. You know, given the conditions at time t equals 0, what are the conditions 1 second later or 1 year later or some other time? Right? Predict the future state. So you can predict a position at a future time. And you can predict a velocity at a future time. If you know where it's going and how fast, you know where it's going to be going at maybe some different speed. If the velocity evolves over time, you'll be able to figure that out too, whether it's going faster or if the velocity, how else can a velocity change? Faster, that's one kind of a change. And slower, yeah. You could be going slower. Is there any other way to change velocity? Well, stopping it, that's slowing it down to zip. Another way to change the velocity. Yeah, direction. You could change the different direction. So if you know how an object's velocity evolves over time, you can predict a whole lot. We call those, that knowledge the equation of motion or time evolution equations. All right? If you know the time evolution equation for a baseball, and actually you guys know one of the two. There's two time evolution equations for a baseball. I showed you one just a few minutes ago. If you know those two equations, you can figure out exactly where a baseball is going, how fast it's moving, and what direction it's moving, where it is, and you can even predict when it's going to land in the bleachers for a home run, or if it's going to land in the outfield and get caught by the center fielder. All right? Or if it's just a little blooper that's caught by the shortstop in the infield, which happens too. All right? So motion is the beginning of what Galileo worked on. Motion in 2 dimensions plus time. All right? Yeah, change of direction is possible if you're working in 2 dimensions. If you're restricted to 1 dimension, you can't really change. You can go faster or slower, but you can't change directions. Well, I guess you can change direction. You can go backwards. You can go backwards or forwards, so that's change of direction. But let's think in 2 dimensions. All right, you're studying motion of an object. It moves between point and point B, point A and point B. All right? Where do you start? Well, the first thing you do is set up a coordinate system. In other words, graph paper. It might be imaginary, but let's draw it in as graph paper. All right, let's draw in some coordinate axes, and I'm parking mine with the origin and the lower left. You can put it with the origin in the middle if you want, or the origin up in the upper right. But this is what I'm doing. All right? And you can call them X and Y, or you can call them Bob and Jim, or anything you want. The traditional names are X and Y for horizontal and vertical. Right? Next thing, you have to decide on the size of your units. Okay, are you talking meters, miles, or nanometers? All right. So in other words, that and the thing about that choice is, it depends on what you're studying. If you're studying human beings in motion, then meters is not bad. Meters per second. Walking 2 meters per second, that's a walking pace. But if you're talking about cities, then miles might be a little bit better. If you're talking about atoms, then nanometers would be a little bit better. If you did your reading, you know that a nanometer is a billionth of a meter, 10 to the minus 9. 1 over a billion of a meter. And let's say that we're working in meters. We're doing some human scale motion, all right? And let's put some coordinates up here, and I actually counted these out. 8,16 for point A, and 44,24 for point B. But if you're taking notes on graph paper, you can put it, whatever your graph paper says. All right? So so there's our coordinates in the XY system. Go ahead and draw a straight line between them. Very first thing to do, or the very first thing that you can do if you want, is to measure the straight line distance from point A to point B. Very basic information. All right? So to figure out that distance, you draw in a right triangle. And if you're working in 3 dimensions, X, Y, and Z, you do a right triangle twice, 2 different right triangles. And it works out, and that helps you get it. But in 2 dimensions, just 1 right triangle, that's all you need. So let me park it down here. All right. And let's see, what's the difference? What's the width of this right triangle? The one that I have. How many blocks is it across according to the coordinates? Yep, it's 36. 44 minus 8. And how tall is it? What's the vertical size? The right? Yeah, that's right, 8. It's 24 minus 16. All right, so go ahead and label that. All right. And if you want to read more about triangles and other shapes, like ellipses and stuff, we'll talk about those occasionally. I'll point you to the appendix, triangles and other shapes. But yeah, this one's 36 meters by 8 meters. So the distance is just the square root of this quantity, 36 squared plus 8 squared. Okay, so that's from, the Pythagorean theorem, a squared plus b squared equals c squared. So d is the length of the hypotenuse, all right? So d squared is 36 squared plus 8 squared. So d itself is the square root of that stuff. And that's the square root of 1360. Works out to about 36.9. Take your calculator out and just verify that. And you guys, it's good to bring a calculator to class every day, because we'll be doing calculations. Not very fancy, not very tough ones, but it will be handy to be able to say, oh yeah, okay, I verified Dr. B. Because every once in a while, I get tripped up, and because I'm rushing too fast or something. And Darian's over here, yeah, that's right. Dr. B gets tripped up. And because she knows I do get tripped up every once in a while. But if you catch me napping, good. But you can't catch me napping unless you have a calculator. All right, so just start just put it in your knapsack and it'll be ready there every day. All right, so here's your calculation. 36 squared plus 8 squared, that's equal to 1360. And you square root that. And that works out to 36.9. And I usually put the symbol M for meters at the end. I don't put it inside those big square roots. Some people do, but I usually leave it out till the end, till I'm finished. All right? All right, so there's your distance, and that's a basic measurement. Actually, that's a basic calculation. Your measurement is the coordinates, and then the calculation is based on the differences of the coordinates. Square them and all that stuff, then takes the square root. Now, that's just the distance as a crow flies from point A straight over to point B. But if you're going from point A to point B, you might not actually be going. Matter of fact, I challenge anybody in here to walk a perfectly straight line. And I bet most people in here could be close, but not perfectly straight. So you might go on a little bit of a curved path. All right, so go ahead and trace that in lightly. All right, you might have something like that. Let me park it down here now. You might have a segmented path like this, a set of 3 line segments. That would be like a robot. A robot would move along straight line segments. And this would be more like a human being down here, this kind of curvaceous path. All right, so, but, theoretically, you could go straight across. Another thing we don't have on this path, we know the distance between the endpoints. I haven't really spelled out what kind of a path. And the other thing is, I haven't give you any kind of time stamp. All right? I don't tell you what the elapsed time is. I don't tell you what the time is at the midpoint. All right? It's easy to identify the midpoint, but that's only if you know the path, and we don't know the path. So I can't give a midpoint time if I don't know a midpoint. And anyways, theoretically, you could say, all right, the time at point A, the clock reads 1:22:08. All right, and then at point B it reads 1:22:47. All right. What's the elapsed time? 39 seconds. All right, so your elapsed time is t subscript b, the time at location B, minus the clock measurement, the clock reading, minus the clock reading at point A, whatever that was, and it's 1:22:08. So the difference is 39 seconds. Now here's another thing that we don't know, but we would like to know. Does the speed change? Is there a time evolution equation for the speed? Is it accelerating? Is it getting slower? Is it getting faster? Is it changing direction? Well, if it's on one of these other paths, a segmented path, it changes direction twice. It changes direction here, where the second segment starts. It changes directions here, where the third segment starts. And down here on the curved path, it's changing direction constantly, all along at every instant of time, right? But then up here on the straight path, if it does go from point A to point B, like a dragster, it still might be accelerating, but we don't have any of that information, right? But we would like to have that, all right? So here's a rundown of what we need to describe and to predict the future state. Positions and distances in meters. That was the first thing we did. And then times from the clock. And then elapsed times from subtraction. Right? And then we need directions at each time. So for the straight line, we just need one direction. But for the segmented line, we need 3 directions. And for the curved line, we need a whole lot of directions at every instant of time. We also need the speed at each time. All right? And even the straight line segment, if you think about it, a dragster that goes on a straight line, for instance, it's accelerating all the way through that straight line, from the starting line to the finish line, hopefully. All right? And so you want to be able to say that. And if you do, you can figure out the velocity at every instant of time. Then you can figure out its future state. All right? So those are the information. And this is the stuff that Galileo and later on Sir Isaac Newton really organized into mathematical laws. Now, the speed is a quotient. Let's talk about this. Speed, customary symbol is v. Delta x over delta t. Now, you may be saying to yourself, Dr. B, what is delta x? That's capital delta in the numerator, delta x, and capital delta t in the denominator. Right? Now, the distance between 2 points or 2 events is usually symbolized delta x. The difference in the 2 x coordinates, all right? And I'm emphasizing the word difference. Capital delta for D, D for difference. Right? So whenever you see delta, that means you've got, like x2 minus x1, or xa minus, or xb minus xa, or x final minus x initial. X subscript f, that usually symbolizes final x coordinate. X subscript I, initial x coordinate. Right? So delta x, and it's just a distance along the x-axis. Right? So a speed is going to be some kind of a delta x in the numerator, or maybe a delta y if it's in free fall. And then in the denominator, a delta t. Now, delta x could also possibly be the hypotenuse, and actually that's what we're going to use. We're going to use the straight line segment, and we know the distance. It's 36.9. And so that's going to go, so that's not, technically that's a combination of delta x's and delta y's. All right, but we're going to use that for our distance in the numerator. And then delta t is the elapsed time. Okay, so that's the difference in two clock readings. So you read your clock at the start, you read your clock at the end, and then you subtract the initial from the final, and you get the elapsed time. You know, so in this case, what was it? 36 seconds or something? What was the elapsed time? 39 seconds, okay. All right, so delta t is, and you guys, it's always later minus earlier. Make a note of that. A delta anything is usually later minus earlier. All right, so if you're talking, you know, the later point, that might be x2 at time t2. And or it could be the final minus initial. So t subscript f minus t subscript I, that's, you know, you look at the clock at the start, and you write it down. You look at the clock at the end, you write it down, and then subtract the first from the second. T subscript f minus t subscript I. So for, in this case, it's 39 seconds. All right? So the speed for this baby, let's calculate it out. All right, here's my formula. I'll make it a little smaller. You get a little room to roam here. All right, so here's my calculation. 36.9 meters. And this is actually along the hypotenuse. And 39 seconds elapsed time. And if you calculate that out, go ahead and calculate that out on your calculator. See if you could verify me. And just keep your calculators out. Let's see, what do we got here? About, it's going to be less than 1, so it's like a 0.9 or something. What do you got? What do you got? Did you do it? Yeah. Good. 0.946. Anybody verify? Raise your hand if you verify. Okay, good. Good. Yeah, so there's your speed. Hey, you guys, that's kind of a pokey speed. Go ahead and make a note to the side. 1 meter, this is a little bit less than a meter per second. 1 meter per second, 1 straight meter per second, that's about 2.24 miles per hour. Okay? So if you ever have a velocity in meters per second, just multiply it in your head by 2.2, 2.24. I know you get an estimate of the speed on the, you know, on your speedometer in your car. All right. Now the distance formula is based on this. All right. So here's the velocity formula, average velocity or average speed, delta x over delta t. Now the distance you go is delta x. So if you cross multiply, you can figure out the distance traveled. All right? So delta x is equal to v delta t. And that's just cross multiplying. From the definition up there, v equals delta x over delta t, and then just cross multiply. In other words, get the delta t over to the other side. And you have v delta t over there. And the numerator is still delta x, but it's by itself. It doesn't have a denominator. Right? And so you can figure out how far something's going. If you know its speed, and you know how long it's going. And so that's like saying, okay, if you're going, it really is this easy. If you're going 55 miles an hour for 1 hour, how far can you go? 55 miles, right? Speed times time. If you're going 55 miles an hour for 2 hours, how far do you go? 110, speed times time, right? So they're all related by that. Now, homework 1. Oh, would you guys like to dismiss early today? Okay, good. So before we dismiss, let me just point out, we have syllabuses up here in front. All right, the greens, can you get those out of the stack there, Darren? And if you want, we have an extra 10 minutes, so if you want to double check that you're on the roster for clicking, that you're registered and stuff, come on up, we'll double check it for you. Homework 1 is due on Thursday, a little bit of calculating. Go ahead and take a look at it, and I'll see you on Thursday. You are dismissed. Can you bring the lights up?
Is it 2.24 miles for average speed?
Yeah, it's about 2.24
Okay, thank you.
for every 1 meter per second.
Okay.
Mike.
La la la.
I was, you emailed me yesterday saying I wasn't on the roster.
What is your name again?
Katie,
I just purchased mine today and the participated in it.
I was the one that was out for surgery.
Yeah,
Katie.
Katie.
Like Katie with an A.
I thought you were in the online section. All right. Let me.
Register with the clicker.
Yeah, that's one of
Ooh,